All right, everybody, welcome on in. So we're going to get started today. Math 3, Intermediate Algebra, continuing where we left off. So looking over things, it looks to me like usually, let's see. So usually people have a little bit of difficulty with absolute value equations and absolute value inequalities. But looking over the homework, many of you have completed those with 100%. So I will interpret that as meaning you don't really need me to go over those, which is part of what I was going to go over today, but then I saw most students have already done it and completed it. So what I'm going to say is kind of a repeat of last time. If you want me to go over some of this stuff because you're stuck on it, by all means, send me the question. But by looking over the grades, it seems to me like students are being successful at it. So unless I get a question, oops, let me change some settings here. It keeps dinging each time someone comes in. Let's see, mute on entry. Yeah, mute on entry and turn off the sound there. Okay. So unless students are telling me they need to go over the absolute value equations and absolute value inequalities, I'm going to assume that you're getting it because it looks to me like you're getting it, okay? All right. So, contact me if you want to go over those. So last time we were talking about exponents, basic exponent rules and going over that kind of stuff. So since we have a little bit of time, since I was planning to talk about this stuff, but it looks like maybe people don't need me to go over that, maybe spend a little time going over these exponent rules and show you how to do those problems just to reinforce what we did last time. And also, you really want to understand exponents well when we move into polynomials, because if you get confused about is this when I'm supposed to add exponents or is this when I'm supposed to multiply them? That's a thing I see on a regular basis. Most students pick it up pretty quick, but there's definitely a population of students that struggle with when to add exponents and when to multiply them. That's kind of the big takeaway from this exponent rules area. Now, that doesn't mean that's all you need to know. Depending on what class you're taking after this one, if you're going into basically anything other than statistics or the topics class, there's a class called math topics, or they changed the name, I think. I forget what it's called. But those two classes don't use a ton of exponents. But if you're going into college algebra, trigonometry, pre-calculus, if you're going the calculus route, any of that kind of stuff, exponent rules, you're going to have to be very good with them. They come up a lot, and you don't really have the it just will take you forever if you have to sit there and think every single time, like, wait, am I supposed to add here or do I multiply? Like I showed you a way to come up with simple little examples to remind yourself. But at some point, you need to be past that. You need to be able to just know, yep, this is when I add the exponents. This is when I multiply them. And then you can move forward from there, okay? So let's take a look at things. Let's go through a few of these problems. And I can just kind of show you how to do it. So oops, let me resize here. That doesn't help. Let me move this up. Oh, then it wants to expand to my entire screen. I don't want that. Just want it right there. Okay, great. So negative exponents. So negative exponents, what would we do? Let's go ahead and write this one on the other screen. So how would we do this? So 5 to the negative 2 over 5 to the 8th. So, oops. So we've got a fraction, which is 5 to the negative 2 over 5 to the 8th equals here we go. 5 to the negative 2 over 5 to the 8th. Let's make that a little bigger. That's a little small. Let's go begin large. And large. There we go. That's a little bigger for us. I think that's going to show up better on the screen. Okay, 5 to the negative 2 over 5 to the negative 8. So generally when you're doing these types of problems, so keep in mind, we rarely ever, in fact, it's almost safe to say never, if you're operating in a math class, it's probably safe to say we never want to leave negative exponents in our final answer. Okay, fully simplified means we don't have multiple versions of the same power to a base, and also we don't have those negative exponents. So if you're putting answers into the computer and you're going, I think mine's like the same as what they're putting in and what they're saying is the right answer, why am I getting it wrong? It may be because your version has negative exponents in it and the actual final version that they want is a more simplified version, where we consider that more simplified when you don't have negative exponents in there. Positive exponents we understand very easily. Negative exponents we have to stop and think about and go, wait, what does this actually mean here? So what would we do? Okay, well, remember, for a negative exponent, we move that piece to the other part of the fraction and it changes the sign. Okay, now people think about this as like magic, like we're just moving things, because we don't write out the steps every single time. But let me show you what we're actually doing, right? So if I go, let's see, that should be center dot, and then what we're actually doing here is taking 5 squared. We're multiplying by 5 squared over 5 squared. So we're taking our original, oops, what's it doing? We got too many slashes in there. There we go. So see what I'm really doing, this is the algebra that a lot of people don't write, and that's fine if you don't write this step out, but you should understand it, because otherwise what it leads to is students just magically wishful thinking, moving things to where they want stuff to be, but not really understanding mathematically why that's okay. We don't ever want to do that, because ultimately what will happen down the road is you'll start to forget what you memorized, and then none of it makes sense, right? It all sort of falls apart. But if you think of it this way and you go, okay, if I multiply the top and bottom of this equation, what do our exponent rules say that we would get? Well, we're going to get a fraction again. Okay, that's legit. So 5 to the negative 2 times 5 squared. Which exponent rule should I be using here? Okay, that's right. That's the one that says we should add exponents, right? Hopefully you knew that already. We add the exponents because 5 to the negative 2 times 5 squared, that's the rule that says add them. So that would give us 5 to the 0. Okay, and hopefully you remember what 5 to the 0 is. We'll talk about that in just a second when we simplify this further. And then what do we get on the bottom? On the bottom, we get 5 to the 8th times 5 squared. Right, so you can see how this 5 to the negative 2, right, it's real easy to go, oh, we just, let me move that down so the thing doesn't pop up. This 5 to the negative 2, we kind of just moved it to the denominator and changed the negative to a positive for the negative exponent, right? Well, yeah, that is what we did. Excuse me. That is what we did, but that's not really a mathematical explanation. If you just told someone, oh, I just moved this to where I wanted it to be because I kind of think that's what you're supposed to do, that mathematically that doesn't really explain it. What we did was we multiplied the top and bottom by 5 squared, and then we get this. So what is the next stage of simplification? Well, 5 to the 0 is 1. Okay, so now let's think about this on the bottom. What's 5 to the 8th times 5 squared? Let's see, which rule am I supposed to use? That is my addition. That's where I add the exponents. So that should give me 5 to the 10th. Okay, 5 to the 10th. And let me remember how they want this. Oh, right. So then they have us choose. So I'm going to choose 5 to the, well, 1 over 5 to the 10th. Submit answer. There we go. Oh, they actually did it differently. That's one thing that I want to make sure you understand about these rules of exponents. There's more than one way to do these problems. So the way I did it was by simplifying the negative exponent and then combining those terms together. You could do it this way, where we have a subtraction rule that says when we have things written like this, you're going to subtract the exponents, which would make it 5 to the negative 2 minus 8, making it 5 to the negative 10. And then what does our rule about negative exponents say? We would move it to the denominator, and the exponent would become positive. So this is not the way I did this problem, but the way I did it is perfectly legitimate. The way they're showing you on this website is perfectly legitimate. They're both totally valid ways to do the problem. So, you know, that's sometimes what's confusing for students is you'll be trying to do the problem one way, and then you'll ask a tutor or you'll ask me, and I'll show you one way to do it, and it looks totally different. And you're like, well, okay, I see what you're doing, but that didn't really help me with my way if I didn't know that you were, say, doing it this way. So that can be confusing for students when you ask someone for help and then they're showing you a different way to do the problem. It can actually be a little disorienting. So just be aware of that. There's more than one way to do these problems, okay? Okay, let's see if these aren't much. These are about the same as the ones we just did. It's just you have a little simplifying to do in the meantime. Okay, let's go to... these are just using those basic operations. This one should be multiplication, so this should be k to the 18. Right, and we go, yep, that's where you're supposed to multiply. They write it out the same way I do, where k to the third to the sixth means that you have 6 k thirds. Well, each one of those is a k, so you multiply it all out, you get 18. Right, just kind of a reminder of what we did last time. Okay, so those aren't too... Let's see what the next one looks like. Yeah, those are just the same. You're just going to be doing some quick problems here. Variables and coefficients. Okay, now it starts to get a little bit more complicated. You have to pay attention to what the exponent is applying to and what the exponent is not applying to. For instance, here's a common mistake that I'll see people do. Let's get a little space here. Okay, so here's what I'll see people do. They'll go 2x to the third equals... Oops, that's not what I want. I want $sign. And they'll say, okay, 2x cubed. All right, well, if I cube everything, 2 cubed is 8, and then I've got my x cubed, and they'll do this kind of a thing. So hopefully most of you are looking at this and going, well, that just looks completely wrong. Why would I think that's right? The problem here is people don't realize this cube is only applying to the x, and they try to apply it to the 2 as well. So this is wrong. I want to make sure everyone understands this is a wrong way to do it. Okay, that's not correct. This exponent is not applying to the 2. When you're thinking about it that way, it should look like this. 2x cubed. Okay, in this case, because there's the parentheses, everything in the parentheses is being raised to the third power. In this case, yes, this would become 2 cubed x cubed, which then equals 8x cubed. So you always have to ask yourself, what is the scope of the exponent? Here, the scope of the exponent is only the x. It's only applying to the x. Down here, the exponent is applying to everything in the parentheses, which includes the 2. Okay? So, think about that. Here's another mistake I see regularly. Is we'll have something like, say, a fraction. And I've got something like 8x to the negative 5 over x cubed. And they'll make that same mistake I just talked about, which is by saying, okay, well, here I have a negative exponent, so I'm supposed to move all this to the bottom, right? And then they'll do this. They'll say this equals, if there's nothing left in the numerator, then remember it's always a 1. But so this is wrong. What I'm showing you is the wrong way to do it, but I'm pointing out because students will try to do it. And then saying, well, that negative exponent, let's move stuff to the bottom, which would give us at the bottom x cubed times 8x to the 5th. And the exponent would become positive now, right? This is a thing I see students do all the time. Except this isn't right, is it? Because this negative exponent is only applying to the x. It's not applying to the 8. So again, just to make this clear, I'm going to say this is wrong. So there's no confusion. That's the wrong way to do it. So if the negative exponent's only applying to the x, then the 8 should have been left, right? So the right way to do this problem looks like this. Okay, so see, I've moved the x to the net with the -5 down to the bottom, making it positive. But notice how the 8 stayed up here because the negative exponent is not applying to the 8. And then now we would just simplify this out. Now it's easy, right? Most students can get it from here, where you'll have 8 over x to the 8th. And that would be your full simplification there. Those are a couple of common mistakes that I see students do. So I want to point those out in case there's any kind of confusion, okay? Okay, so what's going on here? Well, let's just, we don't really call them like terms, but let's think about what can be multiplied here and what can't. Well, we have a -4 times an 8. So what's that going to leave me with? That's going to leave me with a -32. And remember, you can always ask questions in the chat. So as I'm moving through these, if you don't understand something, let me know. Okay, so -32, that's -4 times 8. And then I have q to the 3rd times q. And here's another mistake I see often is students will go, oh, well, I'm supposed to add exponents, right? So I have a 3 here, and I don't have anything here, so 3 plus not anything would be 3, right? Well, no. If you have 3 q's over here, and then you multiply by another q, you get an additional q. You have q to the 4th. You will wait, but there's no exponent here. Remember, when there's no exponent, the exponent is a 1. Just think of it as an invisible 1 on that variable. So we're really adding 3 plus 1, which would give me q to the 4th. That's the right way to do it. And there we go, right? So see how they put the 1 here? They put that 1 there to remind you that it's 3 plus 1. Sometimes people make it 3 plus 0, but that doesn't make any sense, right? Let's see what the next one looks like. Okay, these aren't too bad. So we'd have -7 times 7 is -49. And remember, this negative out in front that's on the coefficient, that doesn't relate to negative exponents. Sometimes students do that where they, now that we've learned about negative exponents, they start mixing up negative coefficients and negative exponents. Those things do not interact. Okay, the negative coefficients work just like they always did. Negative exponents are a totally different subject that works in a different way. So this would be -49z to the 5th. Yep, and there we go. Okay, I think hopefully you get the sense of how that works. Okay, so let's look at, so you've got some basic exponent rules. See how there's parentheses here, so you have to figure out, wait, is the 3 just applying to the a or is it applying to the 2? No, it's not applying to the 2, only what's in the parentheses, right? So this should be what? This would be, well, we're going to get 2a cubed on top, 10a to the 5th on bottom. So just simplify piece by piece. 2 over 10 will leave us with a 5 on the bottom. And we'll, if we have 3 a's on top, 5 on bottom, that gives us a squared. And then people sometimes will leave this blank or they'll put a 0 there. Remember, it's not any of those things. If there's no terms up there, that generally indicates a 1, unless you know that it's a 0. But we don't have anything to indicate it's a 0, right? It's, if we're dividing, when you divide things out, if you divide something by itself, you're left with a 1. So we should get this, and there we go. So they just go through and show you how to go through that problem, okay? Let's look at ones a little harder. Okay, starting to get a little more complicated now, right? A little more complicated. Let's see, what do we have? We have 12a to the 5th on top. What do we have on the bottom? We have -4, a to the 5th to the 4th. So for first question we should ask ourselves, am I supposed to add those exponents in the bottom, or am I supposed to multiply them? So I'm going to give you a couple seconds, just in your own head. Try to decide, am I adding those exponents or am I multiplying them? Hopefully you said multiplying them. Okay, so that's what we're going to get. We're going to get 12a to the 5th on top and negative 4a to the 20th on the bottom. That's a lot of a's, right? But that's okay. We just follow these rules. So 12 over negative 4, that's going to give us a negative 3 on top. Remember, we don't generally want to leave the negative in the bottom. So negative 3. And then what are we going to have on bottom? How many a's? We have 5 a's on top, and we just justified that there's 20 on bottom. So when I go through and cancel them or I subtract them, right, we're going to end up with 15 a's on the bottom. So a to the 15th. Again, if there's any questions on this, speak up. And there we go. So I think they'll take it either way. If you put the negative out in front of the fraction, it'll take it. Or if you did like I did, where you put the negative in the numerator, both of those are considered correct. Your math teachers don't like it when you put negatives in a denominator. They get all, to me, people make a bigger deal out of it than they should. But that's a common thing. So when you get to college algebra or trig, you might have a teacher that sort of weirds out if you put a negative in the denominator. So just be aware of that. Okay, express the following fraction in simplest form using only positive exponents. So we're supposed to simplify this whole thing. This one's complicated enough. I'm not going to just visually walk us through it. We're going to do it in this other problem. So let's take a look over here. Let's go to a new page. Start a new page, brand new. Okay, and it is 12x to the negative 2 on the top. And 3p to the negative 1, x to the negative 5, and was that all to the third? 3p to the negative 1, x to the negative 3. Okay, negative 3. So a lot more rules you got to keep track of here. And sometimes students get stuck with not knowing, well, what's the next step I'm supposed to do? Well, remember, there's more than one. So as long as usually there's more than one possibility, or often there is. So as long as you're using a legitimate choice, you're good. You're good to go, right? If you can just ask yourself, what is a thing that I can do? Oops. This is not right. I have hold on, I have a bracket out of place. Let me fix it. That's not right. Let me delete this part. See if that fixes it. It will if I put parentheses here. There we go. Okay, does that look like it's supposed to? 12x to the negative 2, 3p to the negative 1, x to the negative 5, all raised to the negative 3. Okay, we got it. We got it. Took me a second because my bracket was it was grouping things differently because I had my bracket in the wrong spot. Okay, so lots of ways you can go through this. So if you're watching me do this and going, I would have chosen a different exponent rule, it doesn't mean in any way that you're not wrong, that you're wrong. Your way might even be quicker. You never really know until you work through one of these ways what the best way to do it is, right? Okay, so a couple of choices here about what we can do. I could move that x to the negative 2 from the numerator into the denominator and make it positive. We might want to wait. There's nothing wrong with doing that, but my intuition tells me, why don't we wait and just see? One good thing to do would be to apply this exponent to each of these pieces. Now, a lot of times people use they'll say distribute. They'll say, I'm distributing the negative 3 in here. Technically, you're not. And I know it sounds like semantics and I'm being super strict, but it's confusing because we actually have an operation called the distributive property that involves an addition and a multiplication, right? Notice there's no addition down here. So technically we are not using the distributive property, and it's just really confusing when we say that, because then I go, oh, you're using the distributive property? Oh, okay, that's your mistake, when that's not really what a student means. So we want to be careful not to try not to say the word distribute here, because we're not really doing that. But we can apply this negative 3 in here. So that's going to become, let's see. Probably should just retype it. So we're going to have on top, let's just leave the top how it is for now. And then on the bottom, I'm going to get 3 to the negative 3. I'm going to have p to the negative 1 being raised to the negative 3. And then I'm going to have x to the negative 5th being raised to the negative 3. Let's see if I messed that up bad. Yes, I did. Okay. Let's see. 3p to the negative 1 to the negative 3. Okay, there we go. Sorry about that. There's so many parentheses I have to get in here to get it to format this math correctly. You get one in the wrong place, it messes it all up. Okay, so what I did here was I took this negative 3 exponent and I applied it to each of the things that are multiplying inside the parentheses. So you get 3 to the negative 3, p to the negative 1 to the negative 3, x to the negative 5 to the negative 3. Great, now we know what to do with those. I'm going to be multiplying exponents, aren't I? Right? So let's do that step now. Actually, it still doesn't like something I did here. Do I have one extra thing? There we go. Okay, so now things should start getting a little bit simpler. All right, so let's leave the 12x to the negative 2 alone on top. Now I'm going to get what? 3 to the negative 3. Well, 3 to the negative 3. 3 cubed is 27. So 3 to the negative 3 is 1 over 27. So actually that needs to move to the top. So we're going to put a 27 up here. That's that 3 cubed part. Okay. P to the negative 1 to the negative 3. Now that is where we multiply. Negative 1 times negative 3 is positive 3. So that should become P cubed and then x to the negative 5, x to the negative 3, that should become x. We're multiplying to the 15. Did I copy that problem down right? Seems like a big number that we're going to get here, unless I mess something up. If I mess something up, point it out, but it looks like that number is going to get big. 12 times 27, 324. Now, we have this x to the negative 2. That's going to have to go to the bottom, and it will become x squared, making this x to the 17. So hopefully I didn't mess this up after all that formatting. So on top, we're going to get what? 324. On bottom, we're going to get p cubed x to the 17. Should give us this. So let's see if that's right. 324. Cubed x to the 17. Is that right? There we go. Got it. Okay, so you can see basically the same steps we did. I did this in a couple steps. They kind of did it all at once, but it's the same instructions basically. Okay, so yep, there we go. Let's see what the next one looks like. More of the same kind of stuff. Was that level 3? Oh, that was level 3. Okay, so you should be able to see how to do those types of problems now, right? That should see how to be able to do that. Do recall we have, let's see, it's about to go, let's see, extend. Remember, when we get through the upcoming work on polynomials, we're going to have the exam after that. So just a reminder, the exam is after we do factoring and solving quadratics using factoring. That's when the test is going to occur. So we're kind of up here right now. We've done exponents and scientific notation. I'll talk a little bit about polynomials right now. Then next time we're going to get into multiplying, and the big one is factoring polynomials. Multiplying polynomials is actually not too bad once you get the hang of it. Factoring is difficult, and I mean, like, from a mathematical standpoint, it is difficult. It's not like, you know, people can have opinions about what is more difficult than others. In this case, it's scientific that factoring is harder to do than multiplying. In fact, the fact that this is true is part of how your safety is held when you're online, right? You can take your credit card and put it into Amazon on the internet, and you don't really worry about it, right? Why is that? How is it that someone in between isn't getting your information and able to use your credit card? It's because of encryption, and encryption is literally based on multiplying and factoring. So because it's very easy for computers to multiply numbers, it's very hard to factor them. That's why you might hear sometimes in the news it comes up that a new really big prime was found. Big primes are actually a big deal because they're used in cryptography and coding theory and that kind of stuff, which is a lot of overlap in those areas. They help keep your stuff safe because from a mathematical standpoint, factoring is just objectively harder, right? To do. And that's what makes it safe, is that it's very hard for a computer. Like, basically each computer on each end of a communication takes a really, really large prime and multiplies them together, and the computers are fine with that. Anyone in the middle who intercepts that, tries to factor that, is going to have a very hard time. It could take years to factor that big number because it's just going to be trying primes, and never gets there. So it's actually not worth trying to get your credit card if it means you're going to have a computer running for a year trying to break something, right? So just be aware, factoring is a little tricky. It's not super hard. We're not going to get into cryptography and stuff like that the way that it's used. We'll use the basics of factoring, and we'll talk about it. So polynomials, what exactly are polynomials? Polynomials are one of those things that we'll define it, but also you know it when you see it, right? You see something and you go, yep, that thing's a polynomial. So basically, polynomials have coefficients, variables, and exponents. So one example of a polynomial would be 5x to the 7th minus 3x to the 4th, or 3rd I wrote, plus 2x minus 7. Here's a polynomial. How big is that? That's kind of small. Let me make that bigger. Okay, so I will make the claim, and you might disagree with me at first, but every term in this polynomial, the whole thing is the polynomial. What is a term? I just said term. What does that mean? A term is each of these pieces that's separated by a plus or minus. Those are called the terms. So we would say that this polynomial has 4 terms. 1, 2, 3, 4. I make the case that every term in this polynomial has a coefficient, a variable, and an exponent, right? You might go, wait a minute, I think you're wrong. I look at this. This doesn't have an exponent. Where's the exponent here? Remember, it's a little invisible 1. So there's really an exponent there. We just don't write it. But this is really 2x to the 1, okay? And you go, all right, I'll buy that. But this definitely does not have a coefficient, a variable, and an exponent. And I would say it does, because mathematically we could write this as, think about our exponent rules. We can write that as 7x to the 0, because x to the 0 is 1. So that really simplifies to minus 7, right? So, oops, I'm off the screen a little bit. Let me move that over, I think. So, yeah, and it might seem like, oh, well, that's just some kind of tricky thing. You're playing around with semantics, with the language. It's actually important. There are actually reasons why you need to remember that this x has a 1 on it right here. Recompile. There's reasons it will come up in these chapters why we won't write it, but we'll recognize, yes, this is 2x to the 1. And we will recognize this is 7x to the 0. Okay. One of the first times we need to know that is we start talking about this thing called degree. So again, we don't have to write the x to the 0, but you know it's there, right? The degree of a term in the polynomial is the exponent in that term. So this first one, this is a 7th degree term. This is a 3rd degree term, 1st degree term, and yes, 0 degree term. This term right here has degree 0. Okay. Oops, I should move this over a little more. I thought I moved it over enough. Okay. So we need to know the degrees. Degree 0, degree 1, degree 3, degree 7. What we're usually going to be concerned about is the degree of the entire polynomial. Like, I don't know, 80% of the time, we're going to care about the degree of the polynomial. Those of you who end up in calculus, you'll start paying attention a little bit more to the degrees of each term of the polynomial. So what is the degree of the polynomial versus the degree of the terms? We just talked about the degree of the terms in the polynomial. The degree of the polynomial itself is the highest degree term that occurs in the polynomial. So this polynomial we would say is degree 7 because the highest degree that occurs in the polynomial is 7. Okay, so we'd say, yeah, this is a 7th degree polynomial. That's important because the higher degree the polynomial is, the more complex that thing can be. It can have more terms and curves and maxes and mins and all that kind of stuff. So, so they get more complex. Do you see how I've written this polynomial from highest exponent to lowest? Right, we've got the 7th degree term, then the 3rd, then the 1st, then the 0. That is almost always in your best interest to write them in that form. There are a couple of special instances where we specifically mix up the order. We rearrange the order of the degrees of a polynomial. But I would say 19 out of 20 times, you want it written in this form, where your biggest term, degree term's in front, and then it decreases from there, right? Get in that habit. If you just start from the very beginning writing things that way, it's very easy to do. But I see some students who don't do that, and then later they sort of understand why I want them to write it a certain way, but then it's hard for them to get into that practice. So now just be in the practice of writing them this way when you can. Very rarely we'll turn them around, but we won't worry about that for now. Okay? So we've got our coefficients, variables, exponents. We've got the degree of the terms. We've got the degree of the exponents of the polynomial. Now, your exponents in a polynomial have to be natural numbers, right? Let's see. Whole numbers. So 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. We talked about negative exponents. Negative exponents are totally legitimate mathematically, but not in polynomials, right? So in other words, we wouldn't have this. Like this right now, the way it's written as a polynomial, when I change it by sticking a negative in front of that third power, not a polynomial now. No longer a polynomial. This is, that one term is more like a rational function, which we'll learn in a couple chapters. But just realize no negative exponents, no fractional exponents, which we will actually learn about fractional exponents in a future chapter as well, but not in polynomials. Okay, polynomials should just have natural number exponents here. So nothing weird. No variables in the denominator of a fraction. Can't have that with a polynomial, right? Nice thing about polynomials is they're actually well behaved. I know in an intermediate algebra class or even in a college algebra class, polynomials seem like they're really complicated. But for those of you who are getting to calculus, by the time you get to calculus, you're going to be pretty comfortable with polynomials, and you're actually going to be so glad in calculus when your problem is a polynomial, because calculus on polynomials is very, very easy compared to most of what you do in a calculus course. Like, you're going to be so glad in calculus when you see a test problem and it's a polynomial. You're going to go, oh, great, I know I'm getting this one right, versus the other stuff that gets way more complex. So polynomials are smooth, continuous curves. What does that mean? Well, let's look at one. Okay, here's a polynomial. I just made it up. But see how it's smooth? See how there's no sharp corners or edges or sharp angles? Polynomials are smooth. Okay, that's one of the reasons they behave very well in calculus. In calculus, sharp corners and angles are problems. They're workable usually, but they require a lot more attention. Smooth makes calculus very nice. Continuous, continuity. This graph here does not have any holes in it. There's no breaks. There's no jumps, right? Remember we looked at piecewise functions, I think, a little while ago. There's no weird jumps or breaks or discontinuities of any kind. You could draw this whole thing without lifting your pencil off the paper. That's kind of our real loose way of thinking about this idea of continuity. Can you draw it without lifting your pencil up? Yes, I can. Then it's continuous, right? Those of you who are going to end up in a STEM field, you'll learn more complicated versions of continuity. But for now, just think of it as, can I draw it without lifting my pen off the paper? Here we can. So that makes them very well behaved. They might look kind of weird. Well, that's kind of a weird shape, but it's smooth, it's continuous, it's well behaved. That's helpful for a lot of things. Those, you can make assumptions then about the behavior of this thing by knowing, well, I know there's no weird jumps or anything like that. So just kind of keep that in your mind. Polynomials are smooth, continuous. What is the domain? Right? Remember, the domain is all the x values we can plug into this function. It's everything. Every real number can be plugged into this expression right here, and you will get something back. The range is not everything, right? That's the y values, the outcomes. The range is only from this point right here up, all those y values. So what about approximately negative 1.78 or something and up? But the domain is all real numbers. And that's the domain for any polynomial is all real numbers. You've actually dealt with polynomials already, but you've dealt with special polynomials that we usually give special consideration to. So for instance, consider the polynomial 3x minus 5. 3x minus 5, that's a polynomial, right? It fits our definition. Each term has a coefficient, a variable, and a power. But what does that look like? That's just a line, right? Technically, lines are polynomials. However, they're so much simpler than the higher degree polynomials, we usually treat them separately. But a lot of times that's missed in these algebra classes is that, yes, technically lines are polynomials. They're just very, very basic polynomials. Quadratics, which will be the focus of this chapter, second degree polynomials, those are polynomials, right? So you're already somewhat familiar with polynomials. We're just going to get into more complicated polynomials and talk about them from there. So that's okay. That's kind of your brief introduction into polynomials. Adding polynomials is literally just adding like terms. So any variables that have the same exponent, you can combine those together. The ones that don't, you can't combine together with addition or subtraction. So it's kind of like when we did like terms with just basic variables. Like you could add 3x and 5x to get 8x, but you can't add 3x and 5y because they're not like terms. It's the same thing here. Just look at the variable and the exponent. If they match, you can add those things together. You don't add the exponents in that case. So for instance, if we have 2x cubed plus 4x squared plus 5x cubed plus 3x squared That was weird. Okay, so say I want to add these two polynomials together. Oops, and that's a typo. This should be a 3. All right, I want to add these two polynomials together. Well, look, I have two terms which are x cubed. That makes them like terms. I can add those together. So that's going to give me 7x to the third. We don't change the exponent. Just like when you add a 5x and a 3x, it doesn't change the x. Here we're adding x cubes. We change how many of them we have. It doesn't change the variable. So 2x cubes plus 5x cubes is 7x cubes. And then look at the square terms. It looks like I have 7 of those as well, plus 7x squared. But notice how the variable is still an x squared. Okay, so people get addition and subtraction real fast, especially if you have a couple of videos to watch in the homework. You should be good to go. And then we'll get into multiplication next time, and then we'll start down the road of factoring. Okay, so good work, everybody. I will be, if you're planning to meet me on campus today for office hours, I'm probably going to be 10 to 15 minutes late. My car is being worked on, so I have to ride my bike to school today. Which will take me a little bit of extra time. Hopefully it's not going to rain on me. Looks like it was kind of misting a little bit earlier, but hopefully that doesn't mess me up. So, but if you want to come to campus, if you get there like right at 11, just give me like another 10, 15 minutes. I'm probably going to be slightly late, and then I can help you. Okay. Yeah, I know. My car's being worked on again. It's the same problem. They fixed the thing, but I keep having an oil leak, and I take it in, and they go, okay, we fixed it, and it still keeps leaking oil. So they need to fix it, but I agree. Might be time for a new car. So thanks, everybody. And, yep, so I'll turn off the YouTube stream. Anyone who wants to ask me a question can hop into Zoom. Otherwise, I'll be heading to campus and you can meet me there. Okay, thanks everybody.